morning, everyone. So very briefly recapping the radiation from an ideal surface, okay, and then we will go into solving a problem, and then we will look at the crux of the matter as to why we are doing all of these things. All right. So ideal surface. We looked at this idea last time. Satisfies three things. It's a perfect absorber. Second thing is it's a diffuse emitter. That is, if there is a real surface placed in the vicinity of an ideal surface, then the real surface will receive irradiation in a diffuse manner. Okay? We will develop this idea later on. And the third thing is the ideal surface intensity of emission of radiation obeys Planck's distribution. So we call it as I lambda b lambda comma t. This is the intensity of the radiation emitted by the ideal surface. Emitted by the ideal surface, and this obeys Planck's distribution. Which means that based upon fundamental physics, there is an equation that tells us, okay, if I have an ideal surface, or if I can create an ideal surface, then what is the intensity of the radiant energy that's being emitted by the surface? And the equation that we looked at last class and you can notice that there is no directional dependence because this is a diffuse emitter, an ideal surface. This is the following formula: 2h c0 square lambda to the power 5 and exponent h c0 lambda kbt minus 1. Okay. So here h is Planck's constant, c0 is the speed of light in vacuum, and kb is the Boltzmann constant. We will not be using this equation in its glory, but we will have some tabulated values that we will use eventually. Yeah. Okay. Then we said that, okay, because it's a diffuse emitter and so on, I can calculate the spectral emissive flux for an ideal surface. This is E of lambda comma b, capital E. Once again, a function of the wavelength and temperature. And please notice, this quantity is sometimes also called as spectral emissive power, and the notion of power is power per unit area here. Okay? So this is also labeled as emissive power, spectral emissive power in your textbook. So this is integral, and notice if you have a subscript given and you see that the functional dependence does not have anything based on the direction, it means the integration is done over all the directions. So this is going to be 0 to 2 pi, 0 to pi by 2, lambda comma b, sine theta, cos theta, d theta d phi. But I of lambda comma b is independent of theta and phi, so I can remove it out of the integral, and I eventually end up getting E of lambda comma b is pi times another name for this is spectral hemispherical emissive flux. Hemispherical meaning I've integrated it around the entire hemisphere. Okay? So also called as spectral hemispherical emissive flux or power. Units for I of lambda comma b, watts, meter square, micrometer, steradians, the solid angle, counterpart of the planar angle. Units for the spectral emissive power is without the steradians, meter square, micrometer. So what we have found out is that there is this ideal surface which is more or less well understood based upon fundamental physics, quantum mechanics, and also we have some nice formulas that enable us to calculate the intensity if we so wish, or the spectral emissive flux if we so wish, or I could take the spectral emissive flux, integrate it over the entire wavelength range, and I'll get the total emissive power or the total emissive flux. Okay, so E, B, which is now going to be solely a function of temperature alone, is integral 0 to infinity lambda E lambda comma B lambda comma T d lambda. This is the total emissive flux or power. Once again, this is a notion of power per unit area, okay? And this integration, if you take the blank distribution and then multiply it by the factor pi and then you integrate it, you end up getting the Stefan Boltzmann law. So this ends up being equal to sigma T to the power 4, where sigma is something that we've seen in the past, the Stefan Boltzmann constant, okay? So this is the Stefan Boltzmann law. And once again, mind you, this is for an ideal surface, which means that a real surface is going to emit radiant energy that is a diffraction of the ideal surface. If I can somehow find out that fraction from experiments, if I can make use of the benchmark of an ideal surface from Planck distribution, then I can find the emissive power of a real surface. That is what we are going to be doing, okay? But before that, a couple of plots. So first plot is the spectral emissive flux as a function of wavelength for an ideal surface. Lambda. This is E lambda in watts per meter square. Micrometer. This is on a log scale. And this is a plot that I drew last time. Alright, so these are all curves that you will see. These are for increasing temperature values. So as temperature increases, I keep going higher and higher in terms of the emissive flux. Okay, so this is at some 100 Kelvin. This is, I don't know, some 5000 Kelvin. And obviously you can see that each of these curves, they're going to have a peak value. Okay, and the peak value as you can see is going to keep getting shifted to the left as we travel along the increasing temperature. The locus of all of this is given by the equation of the line, which is called as Is Displacement Law. So the peak value of E of lambda comma b occurs at a lambda is equal to lambda max for a given temperature. So for a given temperature, the lambda max is going to be a particular value. If I increase the temperature, lambda max is going to start reducing because the values are shifting to the left. Okay? For a given temperature, this is obtained by taking the expression for E of lambda comma b, which is this guy here, substituting for I of lambda comma b from the Planck distribution, taking the differentiation of that and setting it equal to 0 with respect to lambda. And the equation that we get is called Wein's displacement law. So I get lambda max times T is 2898 micrometer Kelvin, and this is called Wein's displacement law, and I'm going to write it very quickly as to what it implies. And that line essentially is the locus of all of those points that obey Wein's displacement law. So this line equation is T lambda max is equal to essentially it says whatever the equation is stating. The wavelength at which the peak spectral emissive power occurs is inversely proportional to temperature. That's about it. Okay? It's simple and elegant, but it took a lot of time to discover this. So the wavelength lambda is equal to lambda max, at which the peak spectral emissive power. Once again, please notice this corruption of the word power. I'm talking about flux, I'm not talking about power. This is power per unit area. Okay? Emissive power occurs at some T is inversely proportional to that temperature. And this is in a log-log plot. You can also plot it on a linear scale. Lambda comma b, linear scale, it's a typical scale that we plot things, and the curves will look a little different. Okay? Once again, these are curves for increasing temperature. Okay? And once again, you will see that the peak is getting shifted to the left, but Wein's law is applicable in both the situations. Okay? So at that point, you can always calculate what the value of lambda max is for which the peak spectral emissive flux occurs. Alright. So what are the tools that we have so far? From equations and from physics. We know lambda comma b. If we know this, then we know E lambda comma b and then EB as well. And why this? We know that. So this is completely well understood, and we also know, okay, from Wein's law of displacement, given a particular temperature, what is the wavelength at which the spectral emissive flux is a maximum. So that's the second set of relationships that we will need, lambda max times T, 2898. All right. So just to reiterate these ideas, I'm going to solve a problem. And then we will start talking about real surfaces. And I think after I solve this problem, I also want to talk about an idealization of an ideal surface. How do you create an ideal surface? Is it possible to do one? Okay. All right. So before we solve the problem, but perhaps it makes sense to talk about that now. So how to model an ideal surface. Once again, this is an approximation. Okay, this is not like we're creating one that obeys this completely perfectly well. Even the sun at around 5800 Kelvin only approximately follows the Planck distribution. So if this were 5800 Kelvin, if you look at the intensity of emitted radiation from the sun, it will look somewhat like that. Okay, so it's not exactly the same, but it's close. This is the sun at, I think, 5778 Kelvin surface temperature when it behaves as an ideal body. Okay? All right, so how to create this, or how to model an ideal surface? Fairly simple idea. Take a large cavity with a very small aperture. It's a very small, tiny opening. So this is an aperture, tiny. This is a large cavity. The cavity is modeled as an isothermal surface, so the temperature is the same everywhere, and if the temperature is changing, it is changing by the same amount everywhere within the surface of the walls. Okay? And the basic idea is fairly straightforward. Let's say that a ray of radiant energy enters the cavity through the aperture. So there is a ray that's entering here. What's going to happen? Similar to what a ray of light undergoes, it's going to undergo multiple reflections. Okay, some portion is going to get absorbed, a part of it is going to get reflected. Right? So it will undergo multiple reflections. And what's going to happen is that because this aperture is really tiny and the cavity is really large, this ray of incident radiation will undergo so many reflections that the chances of this escaping out of the aperture is really, really small. And so what this means is that this aperture is acting as an ideal surface because whatever radiant energy is incident on it is absorbed completely. You see the technicality here. It's not the cavity that's the ideal surface, it's the aperture that's the ideal surface. So whatever radiant energy is incident on it is completely absorbed by it because this absorbed or this radiant ray that is passing through the aperture has a very little chance of escaping out. It is just going to keep bouncing off the walls of this cavity. And to satisfy the second property, which is the diffuse emitter, here is what happens. Every ray of light, every ray of radiant energy can be thought of as a packet of photons, packet of energy. Okay? So these packets of energy, they come and then they strike the inner surface of this cavity. They carom off of the surface. In the process of collision, there is a certain exchange of energy. The surface is at a certain temperature, the photons incoming are at a certain temperature or certain energy levels. There is going to be a certain loss of energy or a gain of energy. If the cavity is at a lower temperature, its temperature will slowly increase such that the energy levels are kind of equilibrized or what is called as thermalized. And so at some point in time, the energy of the photons that are bouncing off of the walls of the cavity are completely dependent only on the temperature of the cavity. They are independent of the geometry of the cavity. They are independent of the size of the aperture. Once again, photons are entering here with a certain amount of energy. They hit the surface, there is a collision event, which means that there is exchange of energy. The cavity is at a certain temperature, so the cavity is also emitting radiant energy, which is striking the photons, and there is some conversation taking place. After enough conversation has taken place, everybody settles down, which means that the entire thing reaches a state of thermal equilibrium. And at a state of thermal equilibrium, whatever energy is possessed by these photons that are traveling inside the cavity is purely a function only of the temperature of the cavity, independent of the geometry of the cavity, independent of the aperture dimensions. And if so, if one of these rays are going to escape out of the aperture, they are going to be completely diffuse because they are independent of direction. And as a result, this aperture will act as a diffuse emitter. Once again, this is an approximation, this is an idealization of an ideal surface. So there are, within certain limits, this seems to reasonably work. Okay? Alright, so that's how you create an ideal surface. And what I want to do next is to solve a problem, but before that I need to introduce a quantity called as band emission fraction. I'm going to first write the expression for it and then define it. F0 hyphen lambda is defined as integral from 0 to lambda E lambda comma B lambda T d lambda integral 0 to infinity E lambda comma B lambda comma T d lambda. When lambda looks like a T sometimes, please remind me if it does not look like a lambda. Okay, it has to have a small squiggle. As you can obviously see, this is a fraction, which means that the first letter F represents a fraction. What we are saying here is, okay, I am really not interested in infinite life. That is, I am not interested in things happening between 0 and infinity. Who cares? Most of the time I am interested in radiant energy between a certain wavelength range, maybe from 0 to lambda or lambda 1 to lambda 2, where I could define the limits of lambda 1 and lambda 2. So why am I calculating it from 0 to infinity all the time? Let me pre-record all of these fractions, which I can very well do because I know this guy. What is that equal to? This bottom denominator. Is right up there somewhere. Is the Stefan Boltzmann Law, sigma t to the power 4, so I know this completely. And if I can calculate these fractions, pre-record them for a given range of wavelengths, then I can directly just use whatever I have tabulated instead of going on calculating these again and again, instead of performing the integration every time I need to do it. It's quite painful, right? 0 to lambda. I can do the integration, it's no big deal, but it's quite messy. Okay, you have to have change of variables and so on. So this f of 0 to lambda is called as a fraction of the emissive flux emitted between lambda is equal to 0 and lambda, some wavelength range. Okay. And there is nothing sacred about going from 0 to lambda. I can go from lambda 1 to lambda 2 by doing the following. This is nothing but lambda 1 to 0 plus 0 to lambda 2 that. And what I can do is I can reverse the limits of this integral so that this integral becomes a negative quantity. And so this is essentially the same as integral from 0 to lambda 2 minus 0 to lambda 1 of that. And now if I divide everything by this quantity EB, which is essentially by EB of T, if I take everything and divide it by EB, so this is all divided by EB, which means that these individual pieces will also be divided by EB. Am I making sense to everybody? EB is an integral from 0 to infinity. That's the total emissive power of a real surface over all the wavelength ranges that we're interested in. And so I can say that the first expression on the left hand side is the fraction from lambda 1 to lambda 2. So this is F from lambda 1 to lambda 2 is equal to, this fraction here is from 0 to lambda 2, this fraction is from 0 to lambda 1, so from lambda 1 to lambda 2 I just take the subtraction of the two fractions. Okay, so this represents here. This represents that. And does this make sense to everybody? Yes.
What does that mean between lambda 0?
Oh, lambda could be, so let's say that I want to go from 0 to 0.1 micrometers. Oh, it's an and. Okay, so now let's exercise this formula, for a problem. And in doing so, you would see that for your homework, I have given you a tables. So I have given you a table for the third problem of the homework. The table looks in the following format: 5 columns. Okay. First column is lambda times T in micrometer Kelvin. Okay, so here typically this starts at around 200. Then next value is 400, 600, 800, some range of values. So 400 goes all the way to 100,000, at least as far as I know. In between you will see a special value. What's a special value? 2898. Okay, so these are all the values that this first list will have. You will not be seeing values in your homework until 100,000. If need be so, I will give it to you in the exam or something. Okay. The second column is F 0 to lambda. So, for a given temperature, I can calculate, and for a given temperature and for a given range of the wavelength values, I can calculate whatever is this number here. Okay, so suppose I have to calculate the fraction from 0 to 3 micrometers for a surface, for an ideal surface, that's at 3000 Kelvin, then 3 micrometers times 3000 is 9000. Find that number here, find the fraction there. Okay, it's as simple as that, just picking up values. And you're going to see a problem that we're going to solve. This is dimensionless, as you can see. It's a ratio of two similar quantities or same quantities with different limits. Third one is I lambda comma b divided by sigma t to the power 5 This just tells me that, okay, given a particular wavelength, given the temperature of that ideal surface, what could be the intensity value? Right? Because if I know the temperature, I know sigma T is about 5. If I know the wavelength, I know lambda times T is some value here. So take that value, pick it up from this table. That's going to be this fraction. What is the intensity at that particular wavelength and temperature? Just take this number and multiply that number. Once again, we'll do a problem that will help you understand. Third row is the following. It's going to be relative. So this is I lambda comma b by I lambda comma b lambda max. Okay? And this essentially tells me, okay, what is the relative intensity for a given wavelength and for a given ideal surface temperature. I know the maximum intensity, right? That's going to be happening at lambda max. So for this particular wavelength, what is the relative intensity? And once again, I'm going to solve a problem now that helps understand these things. So let's go to the problem. These are the only columns that we will be using, so we don't need to worry about the rest. So here is the problem. So surface at temperature of 2800 Kelvin. Okay? This is not just any surface, this is an ideal surface. You are asked to do the following. First thing, obtain the fraction of the emissive power emitted between 0.5 micrometers and 1 micrometer. So here lambda 1 is 0.5 micrometers, lambda 2 is 1 micrometer. What is this fraction? F 0.5 to 1. It will obviously not be there in the tables, but I will have two other fractions which I can subtract using that equation that I've just showed you there, and so one can calculate it. Okay? That's the first thing. I'm going to do this step by step. Second thing, for peak intensity, at this temperature, what is lambda max? And of course, what's the peak intensity value? At 2800 Kelvin. And the last one, what's the relative intensity? At lambda is equal to 0.6 micrometers. So let's do it step by step. First part of the problem. Fraction of the power emitted between f of 0.5 micrometers and 1 micrometer. So essentially I'm asked to find out what is f from 0.5 to 1 micrometer. Okay, this is at a particular temperature, 2800 Kelvin. So what do? I say that, okay, this is between two non-zero, the starting point is non-zero, so I have to take the difference between 0 and 1 and 0 and 0.5. So I say that f 0.5 to 1. It is understood that everything is in micrometers, so I'm not going to keep writing that. This is just f from 0 to 1 minus f from 0 to 0.5. To calculate f from 0 to 1, your lambda is 1 micrometer. Temperature is given as 2800 Kelvin. And so what you have to do is multiply the two. Lambda times T is just 2800 micrometer Kelvin 1 times, which is 2800 micrometer Kelvin. Am I making sense to everybody so far? And all I have to do is, if you have the tables in front of you, I sent an email, it's in your homework, number 7, problem 3. If you have access to it, you're more than welcome to open it. All I have to do is go to this table that I'm given, figure out, okay, hey, is there a lambda t at 2800? And it will be probably somewhere close to this value here. So at 2800, what is this fraction? Go to the tables and figure it out. And I have that value there. And so this is, for me, is equal to 0.227897. Okay, this is from the second column of the table for an entry that has lambda times t is equal to 2800. Am I making sense to everybody? Okay, just picking numbers from the table, nothing fancy going on here. Do the same thing for 0 to 0.5, which is lambda is equal to 0.5, t is 2800 Kelvin, lambda times t is 2800 times 0.5, which is 1400. So lambda times t, 1400 micrometer Kelvin. Go to the tables. 1400 somewhere here. Pick out the value, plug it in, subtract, and you will never get a problem like this in your exam. You might, you never know. You get something that is based off of this. So that's 0.007790. Okay, and the difference between the two, I'm going to snake it in here. So f from 0.5 to 1 is 0 to 1 minus 0 to 0.5, which is 0.2201 approximately. So that's the first part. So I'm going to erase up to the first part of this question, okay, so that I have all this in front of me. How do you solve the second part of the question? Yes?
Differentiate and set it to 0.
I could do that, but I have already done that. And I have obtained the formula from Wien's law, somewhere written down there. Lambda max times T is 2898. So that's already done for me. So all I have to do is just plug in T is equal to 2800. 2898 by 2800 is close to 1.0 something. So lambda max times T. Lambda max is the value of the wavelength at which the intensity is the maximum. Please notice that. That's not the maximum wavelength. Okay, this is the value of lambda for peak intensity. This is equal to 2898. So that lambda max is 2898 by the temperature of that surface, which is 2800, that's given to me. That's 1.035 micrometers is the answer. So in the infrared region, almost. So if this were the sun, I would not be able to see. Thankfully, the sun is emitting radiant energy at a much higher temperature. So the peak is going to be somewhere in the visible part of the spectrum. Okay. All right. And it goes to say how beautiful eyesight is in some sense. So for peak intensity, lambda max is found out. I'm going to get rid of that. That's the second part of the question. What is the peak intensity? Two ways to do this. You can go to good old Max Planck, substitute for all the constants, substitute for lambda, substitute for temperature, and figure out I lambda B. Or you go to the tables and you see, okay, I need to find out I lambda comma B as lambda max. So this value is already denoted in the tables. So I go to that, figure out what is this entry here. Does this make sense to everybody? I figure out what that entry is, and then I say, okay, whatever that entry is going to be evaluated at a lambda of 1.035 micrometers for this surface of 2800 Kelvin, because the product of that is going to be 2898. And so if I substitute the third part, I have I lambda comma B lambda max comma T divided by sigma times T to the power 4. Temperature is now going to be in Kelvin. You're doing radiation heat transfer. Forget the degree Celsius. Never use it from now on for any of the rest of the exams. Okay? Everything has to be in Kelvin. Mind you, this is 2800 to the power 5. So this is actually the fraction of the intensity per total emissive power of the ideal surface per unit temperature. That is sigma T to the power 4 is the total emissive power. So this is I of lambda comma B divided by sigma T to the power 4 divided by temperature T. Okay, so per emissive power per temperature. It's just the way it is tabulated. And this is equal to 2898. Am I making sense to everybody? I want to make sure this is all clear. Are there any questions so far? Because from the next time I'm not going to be explaining this table, neither am I going to be explaining the method. We're just going to go very fast. Okay? So I want to be absolutely clear. Alright. So if this is understood, then I just have to calculate I lambda comma B, substitute, and obtain the following value. This is 7.05, and I'm sorry, this is not 2898. I'm sorry. This has to be the table entry from here. Apologies. This is the table entry at 2898. Sorry about that. And the table entry is 0.77722. 0.722 10 to the power minus 4. That's the table entry for the lambda max times T is equal to 2898. Then you calculate this, and this is equal to 7.05 10 to the power 5 watts meter square micrometer stereo. Your typical units for intensity. Okay. Last one. I want to find relative intensity at a particular wavelength. So I lambda comma B at lambda is equal to 0.6 micrometer and 2800 Kelvin divided by I of lambda comma B lambda t is equal to 2898. That is the peak value, or where lambda max value, whatever that is. This is lambda max, which is the value that we just calculated. So multiple ways of doing this. The easiest way is to use the table. You have a column of the table dedicated for relative intensity, and this value is always evaluated at the maximum lambda that you are choosing for the problem. That is at this particular value, and the product of lambda max and t is equal to 2898. So all you have to do is figure out what is lambda times t for the value of lambda you are interested in. Is 0.6 times 2800. This is 1680. It would be nice if 1680 were present on the tables. It most probably will not be, but I will have a value of lambda t is equal to 1600. I will have a value of lambda t is equal to 1800. 1680 is in between these two, so I have to interpolate. Okay? So very briefly, I look at the lambda t entry, other columns. I look at the I lambda b by I lambda b lambda max column. There I will see two entries, 1600, 1800, some value here, some value there. I have to interpolate. You can use linear interpolation. So interpolate to find the fraction of relative. You've done enough interpolation in thermodynamics. I'm not going to do it. Okay? I'll just write down the answer. You have the table with you. I'm going to post my solution as well. Please compare and see. Okay, so the answer will end up being 0.027567. Alright, so at 0.6 micrometers, essentially what it is saying is that the intensity is 2% of the peak intensity. 0.026 is approximately 3% of the peak intensity. That's what it says. So much for this problem. Now in the next 5 minutes, I want to tie this all together up and see where we are in terms of our aims of characterizing emissive power of real surfaces. So real surface. To characterize the emissive power of real surfaces, we need two things. I need the emissive characteristics of an ideal surface. Of ideal surfaces, which we already know from Planck's distribution and all of these formulas that you've seen, that entire first set of panels out there. And I need experiments, experimental data. This is based on spectroscopic studies, and the experimental data will typically give you the emissivity of real surfaces. But it has to be categorized with respect to some kind of dependencies. So this is